Data sharing imposes stringent requirements on collection descriptions. The challenge is how to provide enough information that the data will be reusable without having to involve communication with the collection developer. The types of data sharing that are appropriate for a research collaboration may be quite different from data sharing for a reference collection. The members of the research collaboration may have complete tacit knowledge about the naming, arrangement, description, and provenance of the shared data sets. Users of the reference collection will not have the same tacit knowledge. The challenge is turning the tacit knowledge known by the research collaborators into explicit knowledge that can be used by someone unfamiliar with the research project. Thus, sharing requires capturing knowledge in multiple forms: policies for controlling proprietary data and protected data, policies for managing time-dependent access restrictions, knowledge required to understand the meaning of the data, knowledge required to choose appropriate programs for parsing the data, knowledge required to understand why files are grouped together. The management of access controls is needed even for public data. Even if a collection is made publicly accessible, write restrictions are enforced to restrict changes. Access controls determine who is allowed to replace corrupted files, who is allowed to update a file, who is allowed to add new material, and who is allowed to add metadata. The access controls provide mechanisms for access by different groups of people. Examples of the groups and the associated access controls are collaborators. Each collaborator is given an account in the data grid, and explicit read, write, execute permissions are granted. To simplify management, collaborators are organized in user groups, and the access permission is granted to the group. Other projects. Persons outside the collaboration can be granted access through a ticket, which provides a URL for downloading the file. This type of access is widely seen in email between project members and other projects. Entire discipline. At this point, the data are formally published. Read access permission is granted to the anonymous account, and a URL is created that points to the collection. An example is shown here with a URL for accessing a public collection within the DataNet Federation Consortium. This URL points to a collection in DFC main home, DFC public. Permission is basically given to all the contents of this collection. The description of data within a research collaboration needs to define a complete context. These requirements come from preservation requirements and the NSF Data Management Plan requirements and include the source of the data, known as provenance information, how the data were generated or collected, who collected the data, who submitted the data structure or the file format, the physical variables used in the dataset, the meaning of variables within the data, including physical units, the choice of coordinate system for gridded data. NASA has 4 levels of derived data products generated from satellite measurements. These are the original raw data received from the sensor, calibrated data that corrects for drifts in the sensor properties, physical variables created by converting the sensor data stream, projected physical variables mapped onto a coordinate system. Each level requires processing of the data stream. The context description for each level requires use of an appropriate schema defined by domain experts. The schema should be interpretable by a specified knowledge community. For the SILS Lifetime Library, the domain expert for each collection was the student who assembled the collection. The knowledge community also was the student and possibly friends or relatives. Most research collaborations hold data as proprietary until a publication is accepted. This varies widely. Some groups view their sensor data as public information and make the raw data available immediately. When they create derived data products from the raw data, they impose a proprietary period to enable review of the data products to eliminate possible errors. The length of time for the proprietary period varies from 6 months to a year to the end of the project. Other groups provide access to their data products immediately with the assumption that any problems found in the data products by other groups will more rapidly lead to a reliable data set. To automate creation of time-dependent access controls, a project can save the data creation time, write a rule that makes the data public after a specified time interval, or write a rule that makes the data public after an access approval flag is set on a data object. Examples are provided in Chapter 7.22 of the Policy Examples Workbook. Take 7 minutes to complete Exercise 36. Identify 3 policies related to sharing that would be useful for your research collaboration. Consider the data management plan policies as a possible source. Look at ways the proprietary period is specified in task number 22 in table 7.1 of the policy examples workbook. Please load your paragraph into the lifetime library in the sub-collection class INLS 624 by the end of today's class. The SILS Lifetime Library provides students with the opportunity to create a personal digital library that can be used as a reference collection. Every SILS student should build a digital library and experiment with naming, arrangement, description, and preservation. The SILS Lifetime Library provides the tools for students to try each of these tasks, change their mind, and try alternate approaches. The SILS Lifetime Library is a highly controlled digital library. The control includes the authentication of every access and the authorization of every operation. The control also includes standard rules for automating enforcement of management policies. The policies that are implemented control interactions with technology, such as storage systems and databases, control interactions with users, such as sharing, access controls, and viewing, and control basic properties of the data collection. The SILS Lifetime Library is designed to run with minimal supervision, minimizing the amount of labor needed to keep the library functioning. This objective is realized through the creation of policies that automate enforcement of management tasks. The basic set of properties that are enforced by the SILS Lifetime Library are the following. Access controls are enforced. A student can only access files for which a read permission has been granted. Students can always access files that they own or have loaded into their personal collections. Strict access controls refer to the enforcement of file name viewing permissions. With strict access control, students can only browse file names for which they have read permission. Quotas are enforced. Every student is given a 250 gigabyte quota. The total size of all your files must be less than this amount. Note that replicas are not included in this limit. Since every file is replicated, the total amount of allowed storage, including replicas, is 500 gigabytes. Quota verification. Periodically, the quota limit is checked. When the quota limit is exceeded, you may still read files, but you cannot load new files into the digital library. File replication. A rule automatically replicates each file loaded into the digital library to a storage system at the Renaissance Computing Institute, which is 3.5 miles away from SILS. Replication storage location selection. A replication storage resource manages creation of replicas at 2 storage locations. File checksums. File checksums are automatically created and stored. Integrity verification. The data grid administrator periodically verifies that the required number of replicas exist and that the checksums correspond to the saved value. Usage reports. Statistics about the number of users, the amount of data stored, and the top 10 users are provided to the dean. The policies controlling the Lifetime Library are documented in chapters 2 and 3 of the Policy Examples Workbook. Administrative policies manage properties of the digital library environment. They include management of user creation. For every new user, a home collection and a trash collection are created. User deletion. When an account is deleted, currently the associated home and trash collections are deleted. Data grid renaming. If desired, the name of the SILS data grid can be changed from LifeLab Zone to another name. Network I/O streams. The data grid automatically uses multiple I/O streams for sending files that are over 32 megabytes in size. File registration. Files can be registered into the data grid without making a physical copy. This is controlled by the data grid administrator to avoid security vulnerabilities. Physical path naming. Currently, the file name used in a physical storage system vault is the same as the name used in the data grid to aid recoverability in the case of errors. Execution threads. The data grid administrator can set the number of threads that can be run in parallel on a server. This helps limit load problems for very long-running tasks. Bulk file loading. Controls can be set to minimize the operations performed as files are being bulk loaded. This is intended to optimize network file transfer. Storage resource location. The default storage location can be defined. Currently, this is at SILS for the Lifetime Library on Storage Resource LifeLib Rest 1. Students can implement their own rules for automating tasks related to their personal digital library. The rules can be run interactively or queued for periodic execution. Students have automated synchronization of a local directory on their laptop with the Lifetime Library, bulk loading of metadata for MP3 files, bulk loading of descriptive metadata using a pipe-delimited file of attributes, staging of files from their laptop, metadata searches. This corresponds to creation of a rule to query for specific metadata attributes.